sorry about that. Live stream's back. So talked about this problem, and from here, I want to talk about ultraviolet disinfection. And if we consider our electromagnetic spectrum, I think maybe we mentioned this already this semester, but essentially our visible range is between 400 and 780-ish. It's literally a spectrum, right? So some of the photons that are higher or lower energy, our eyes will be able to see. There's even some variation in how well different eyes, even eye colors. If you imagine color means it's absorbing some sort of light. I've got brown eyes, so that aspect is going to absorb light a little differently than my wife's like gray, green, blue eyes. Which is very interesting that they tend to shift a little bit for some reason. But the molecular composition of even the molecules giving your eyes color may affect this to a slight amount, and then there's like the rods and the different receptors for the light itself. So there is a little bit of natural variation in either the intensity you receive or your light-dark contrast type of stuff. So this is kind of a generality. You might technically be able to see a little bit into the UV, or maybe it just looks like a purple haze sort of a thing and you're not sure, but your eyes are at least detecting some effects. Of course, if you go further, then you really start getting to a point where it's invisible, right? So it's not in our visible spectrum, but it's certainly there. We use infrared light for a variety of things, including heating, keeping food warm, or making a space heater or something. It's literally just putting out a lot of this infrared light because it has a warming effect. When some object absorbs that light, it just vibrates a little bit, right? It's not the same type of action as an ultraviolet or an X-ray or something photon that can then maybe damage the molecule or whatever. It's just causing it to be a little warmer, a little more vibrational energy by absorbing it. So depending on the energy of the light, energy is kind of inversely proportional to the wavelength. If a wave is like this, and then a small wave, a shorter wavelength, it just has a lot more energy in it. So if we think of this as high energy photons, and on this scale it's lower energy, higher and lower is probably a more correct way of saying it. We could even go out all the way to gamma rays and all of that that we associate with radioactivity beyond X-rays, or up from infrared into microwaves, radio waves, and all that. But for our purposes, what I want to highlight is in the ultraviolet range, we have UVC that is germicidal, and we'll talk about that here in a moment. There's also UVB that causes a lot of secondary photoreactions to occur. Some UVA will do that, but a lot of molecules are going to be excited in an electronic manner. So their electrons get jostled about or get excited states or something that causes a lot more oxidation type reactions, because oxidation is you take an electron away from something. If you would excite an electron, maybe you're making it easier to take that electron away. That means it's easier for this molecule then to react with just oxygen that's in the environment. So you're opening up your molecules in your body or in the cell or whatever you're talking about to more opportunities to be oxidized. And if you've ever heard of antioxidants or oxidative stress, this is very much the type of thing we're talking about, is random acts of oxidation, right? Kind of like a random act of kindness or of, I don't know, malevolence or something. It's oxidation, it's attacking random molecules. And by exciting the molecules with ultraviolet light, that kind of UVA and UVB range is primarily the random acts of oxidation, promoting them, right? So that's why we like to have sunscreen, because that will essentially burn us, as that repeat exposure to oxidation is where we get sunburns. There is some cancer risk there in damaging DNA, but really it's the UVC that's a direct DNA damage. I think that in a couple slides I'll explain that. So in terms of our actual germicidal wavelengths that we use for UV dosing for disinfection. It's pretty much UVC. So what maybe I'll summarize here and say direct DNA damage, and we'll say random acts of oxidation. Not violence, not kindness. I guess maybe it's a little bit violent. Okay. So what do we do in practice? Well, a typical UV dosing chamber, at least with our conventional means, with the mercury fluorescent lamps, it's going to look something like this, where we have some chamber that's assembled in a way where we have flow coming through, passes through this channel, and out the other end, because we have a light that is essentially a tube inside. And our reactor designs are generally, at least for these fluorescent lamps, generally restricted to something that deals with a tube. Those fluorescent lamps, as we see in our ceiling, that's kind of the most convenient way to apply them. Yeah, maybe we can bend them or something, but it has to be, the deal is these fluorescent lamps have to be operated as a fluorescent lamp, meaning they have to have essentially an arc of electricity going through mercury vapor to excite that mercury vapor to cause it to emit photons at a specific wavelength. They emit in that UVC range. In fact, the lamps up here above us are emitting some there, but they're coated in this white phosphor stuff that's going to take all that energy and do fluorescence, why we're calling them fluorescent lamps, and fluoresce white light back out, also taking away all the UVC radiation. Not only that, but also the glass itself is going to absorb a lot of it. So then, if not the glass, then the plastic, and if not the plastic, then even just our atmosphere here will diminish UVC pretty well. I would not feel like it was safe if that was a UVC lamp and it's just open. If the plastic in place, we'd be pretty safe. So that's just kind of a little example there for you. So the other thing about this, because glass, so like your standard glass, absorbs that UV light, we have to design this in such a way where we use very fancy glass, which is basically quartz, really fancy fabricated quartz to protect our lamp. So the lamp material itself is going to be a quartz or something similar to keep, that has to be pressurized to keep this, well, it's low pressure, but it's pressurized compared to the environment nonetheless. So low pressure of mercury, and it's essentially containing mercury vapor, and we don't want that in our water. We don't want that, to be exposed to that. So it has to be sealed, and then we need to protect it from whatever is in the water, because there's inevitably going to be some organic matter and stuff that starts collecting on the surface of this bulb, and to clean that off, we risk breaking the lamp, which is costly and is then going to expose it to mercury. So what we do is we actually have if this here is our lamp itself, then what we'll do is we'll have a protective quartz sleeve that goes around it. The light will shine through, and this will be what's exposed to the water. So let's say it's a quartz sleeve, and then you'd have to take that sleeve out every now and then and clean it. Now you can scrub it, and in fact I think that in practice typically you do have to physically scrub it, and I think it takes a lot of effort and work, which means if you're scrubbing it, this is fragile quartz, you might break it, which is then a big cost. Okay, so you could probably chemically clean it to an extent, but it's going to be a combination of like mineral type deposits, a lot of organic matter. If you think about, like, you leave a little coffee stain on the counter and you get this like brown gook that's all that organic matter that was in the coffee, right? And it's going to be a lot like that over time, especially because this light is providing, like I just said, all that energy for different oxidation reactions to happen with this organic matter. And if the organic matter likes to stick on the quartz, compared to being in the water, it's going to accumulate there. Now, not all organic matter is going to like the quartz, but enough of it will, and there's going to be a lot of chemistry happening, so there's just going to be a buildup eventually of gunk. And so that's going to block the UV light. And so we have to clean that eventually. That's a significant routine maintenance cost. In fact, it has seen one interesting development fairly recently, where there's the possibility to use a plastic here and kind of reverse the system. I guess you could use a quartz this way, although that it might be too fragile to do a large system like this. But there's a plastic that transmits most of the UV, not all of it. So it's not, you're having an efficiency drop because only like 80% of the light gets through the plastic compared to near 100% of the light gets through the quartz. So, but here's an idea where you shine the light into the tube from outside rather than shining it from the middle outward. And so then you have this plastic, I think it's a very special acrylic, so PMMA, polymethyl methacrylate, I think, is the polymer. But it's fancy so that presumably it's resistant to any UV damage that might happen, because again, just like those organic molecules around, if there's anything in this organic polymer that would be excited by the light and could be oxidized, well, you risk damaging the polymer itself with the ultraviolet light. So at 254 nanometers, which is our common mercury lamp, it has decent, something like 70% transmittance. Okay, so that's a potential option, and then it's a lot cheaper to replace a plastic tube. It's a lot less fragile, and so presumably you can clean that a bit easier and have lower maintenance costs by having your lamps outside instead of inside. Now, there's another consideration. You might be losing a lot of your photons here going somewhere else. So maybe you have to have a reflector, which you're going to have some losses, or maybe you make a lot of these pipes going through instead of just that one. But ultimately, the idea is whatever you're doing and however the maintenance happens, what you want is your water to be in contact with your ultraviolet light. Because it's going to be like a plug flow reactor, sort of, right? Because the water is going to be coming through the system and going to be exposed to some amount of light during that time. There's going to be some variability. The water right next to the light is going to probably get more light than what's furthest away. So generally we design based on the amount of light that the furthest corner of the reactor gets. So we kind of design based on the worst case scenario of how much light is that receiving. Once we do that, then it's a lot like a chemical disinfectant. We have some dose. It's going to cause some specific lethality with our microbe. We talked about that last time, is that coefficient of specific lethality between like some chemical, chlorine or ozone, and some microbe, whether it's E. coli or salmonella or whatever. So we'll have a similar outcome like that, where we know the DNA is going to be damaged, and it's going to be, some organisms are slightly more or less resistant, and it's going to go in that manner. So here's just an example from a lab. Sometimes we'll use a UVC light behind a biosafety cabinet to keep this space that you're going to work with microbes sterile, or as disinfected as you can. And it turns out that the little pane of glass there protects anybody in the laboratory just fine from that UVC light. And I've tested this many times in my own lab because I've dealt with these, and I'm a bit of a photochemist, so it's like, oh no, how bad is this? But I have a little detector so you can actually physically see it and measure it in action, which is kind of cool. So that's ultimately what it looks like. And the light that we're seeing there is not, can't actually see the ultraviolet portion. It's just emitting some in the visible as well as the ultraviolet. It's pretty common. Even if it was emitting only just the UVC, then there's probably some things around it that are going to fluoresce given that wavelength. So even if you couldn't see it at all, something will probably shine brightly, like a black light. If you're ever doing like cosmic bowling or whatever, like the black light will illuminate certain parts of your clothing or something that happens to be fluorescent. So definitely with the UVC, that's likely to happen. Okay, so a little more specifics here then. We've been talking about these mercury lamps. Well, probably the most common is a low pressure mercury lamp. Sometimes larger applications will use what's called a medium pressure, but the low pressure gives this really nice spike right at 254 nanometers. So that's a very commonly known and studied wavelength. And if you notice, this low pressure mercury lamp basically doesn't produce hardly anything below that, almost nothing above it. There's a couple little spikes here, and tends to, even in the blue range, it has a little bit up there, kind of as we saw visually a moment ago. But it's almost all 254, and it's a pretty narrow peak. So it's very helpful in a way to understand, okay, what is this wavelength doing? It's really a slight range. But if we compare that to what we would call our germicidal effectiveness curve, this is essentially where DNA absorbs light. We see that DNA is absorbing light pretty well in that range, right? And that means it's going to be effective at causing DNA damage. We can also see that if we define UVC as kind of anything below about 280, then the germicidal effectiveness, most of that's in that UVC range, but we do have a bit of potential. If this is UVB between 280 and 320, there is some effectiveness, right? So there is some potential for that direct DNA damage from UVB photons, even if it's not a whole lot. By the way, sunlight will kind of do something like this, where it's tailing off to just about nothing, maybe even more severely, something like that, as it gets down near 300. Okay, so we get a little bit of UVB, especially if our UV index is high. That means a fair bit of UV is coming through, and so we have a little bit of overlap there, giving us some carcinogenic concerns. The alternative, a medium pressure lamp, is not quite as efficient on a photon basis in terms of germicidal effectiveness, but I think that the operational energy gives some savings. So I think it's a little cheaper in terms of power applied to the lamp to get a really high-powered light source to use medium pressure. So it's really justified in certain cases where you really need a high-power lamp and you have a big operation going. So it's not typical for small-scale systems, and even large-scale systems. I think some of them use low pressure, so it's occasionally used. Typically high-power cases. So it would not be something you'd use for like a portable device, for example. Okay, speaking to that concept of that germicidal effectiveness curve, here we have an interesting plot where we see this black line is DNA absorption generally. It's sort of a general drawing, in a sense, a concept. If no one DNA is exactly the same as, like, from one organism is exactly the same as DNA from another, right? So DNA is going to be a little different based on where you're looking at it and all that, but on average, the molecules that comprise DNA are going to absorb something like that curve, absorb light in that manner. So then you take a look and see, okay, well, how effective or how much light is being absorbed. This is intensity, the amount of intensity absorbed at a given wavelength, and then you measure that for different organisms. We see that roughly these are the different organisms that are measured. We've got this virus MS2, and then we have Cryptosporidium parvum. We've talked about Cryptosporidium. I'll get that quiz to you pretty soon, and maybe I'll just go ahead and do it on Moodle, so you'll have that available. But for these two, you can see, oh, they're absorbing approximately near that line. So that's pretty helpful, and that's giving us some indication of how effective the UV light's going to be. There is a little caveat here. Turns out UV is a lot more effective on bigger organisms because there's a lot more DNA that can be disrupted. So if you've got a big organism, lots of DNA in it, and you've got the same amount of light passing through, the random chance of that organism absorbing light and having a sterilizing impact, since you have so much more DNA that could be damaged, it's more likely. Whereas if you have the viruses, much more of them, and they're all smaller, it's just less likely that the photons passing through happen to destroy it or damage them. Okay, just a little bit of the same concept here, except this time it's an activation rate constant relative to that 254 nanometers. So if our standard here is this is exactly 1, that's how they've drawn it, at 254, then if we go a little bit to the 265 range, we get an increase. Most other places we get a decrease, and of course if we're just going down higher and higher energy, that tends to just disrupt things altogether. So kind of one other way to look at it. And another note here is if we get a different wavelength source, we can see if we could identify the ideal wavelength, it might actually be right around here. And it turns out we have some LEDs in that range that could potentially give us a boost in the germicidal effectiveness. So one of the things I've been studying a lot is how do we make the best use of an LED UV source compared to our conventional methods. Okay, so the way DNA is damaged during UV disinfection is primarily what we call dimerization. So we have a DNA molecule, so all these base pairs lined up and connected to one another, and a lot of the DNA damage happens between two thymine groups, and if you want to call them a monomer, so a single molecule, what's going to happen is they'll dimerize. Dimer meaning two, and mer meaning, or di is, dimerization is two molecules becoming one, essentially. So the Latin roots di is two, and mer is kind of molecule. So two thymines will then, because they've absorbed the energy, they become a little bit reactive and will then react with one another and stick together. And it's a lot like you took some super glue and put a dot of it between two zipper spots on one side of the zipper, right? Two of those little notches. And then you try to zip up or down, it's not going to pass it because it can no longer function there. It's just not going to mesh with the other prong that's trying to go in between. So that kind of throws a wrench in there. Now, a lot of organisms have some capacity to repair that. There's one in particular that, if we have time, I'll talk a little more about, but it's called photoliase or photoliase. It's an enzyme that's actually driven by light, and some bacteria have it. And if they do have it, and they're being exposed to light that's blue, kind of blue wavelength, or maybe even into the UVA, that light actually propels this enzyme forward. So it's kind of an automatic system. If the organism knows it's being bombarded by intense light, this enzyme will be churning through the system, repairing, kind of undimerizing any of these thymine dimers. There are a few other dimerization or damage instances. I think there's some that could cross and cause two that are across that barrier to stick together. But the thymine ones are kind of the most common, so it's a good example there. Okay, another kind of showcase of that. If you have some normal DNA on the left and then it's replicating, it's kind of splitting apart. That's all well and good, but then when you have that dimerization, it kind of gets to that spot and gets stuck, and it can no longer continue replicating. So this is why you could have You could dose a microorganism with ultraviolet light, and it could be happily living its best life, except that it can't replicate, can't reproduce, and it can't produce more of the DNA in that manner. So you could have a sterilized cell. It's alive, but sterile, meaning it can't replicate. Okay, so kind of back to practical applications or implications. Well, what are the important factors involved with knowing how much light our targets are going to receive? Well, first of all, we want to know how much light is going to make it through our reactor. And so that's one of the main sources of concern here would be particulate matter. So again, why we do all the sedimentation and all the particle removal steps before we get to disinfection. It's important for the chemical disinfectant because maybe an organism is hiding inside a particle and the disinfectant can't get there. And likewise, if we're shining light through the system and trying to contact the bacteria or the virus with light, well, a few descriptions here, you can see we could have particle light refraction. So it's sort of like as light passes through something, the refraction means it's kind of like that prism effect. It's shifting a little bit. If you look into a swimming pool, you'll notice, let's say you have you either you put your arm in it or you have like a cleaning pole or something with a net at the end, you'll see the light is refracted, and so it looks like there's a sharp angle change. You know in your mind that this is going straight. You put a straight pole or you have your arm straight. It should be straight, but it looks, tilted one way or the other. That's light refraction, right? So that could happen, cause some avoidance of a microbe could potentially avoid the light that way. You could have reflection. The light's not making it through the system. You could have light scattering, which is something sort of between those two effects in that way. So in any case, we don't want that. So we want to remove the particles. So if we do have turbid water, if we weren't able to treat it for particle removal, then we're going to have less effectiveness, or we would need to dose it to a higher extent. One of the other factors here is something I mentioned already, light absorption by other stuff in the water. So if we have organic matter, or even let's say you put food coloring in the water, right? That's going to absorb light. That's why we can see it. Well, if there's something in the water that's absorbing light, that's molecular absorption, not scatter, not reflection. It's just a molecule taking that light and being a little higher energy for it or whatever. Our clothes, the dyes absorb certain light so that what we see as a result is some color, right? Well, if that's happening with ultraviolet light, then that's going to cause a reduction in the amount of light going through the system. And this is a very well-known law of photochemistry. Technically, you could think of it maybe as physics or as whatever, but it's one of our laws of photochemistry. And this is known as the Beer-Lambert law. And that means, what that implies is that if we have some incoming light, so of some intensity, I naught, and it travels through and results as some I final through some length here, then we know that the concentration of absorbing molecules is proportional to how much light is reduced. Okay, so it's just meaning like the more dye, the more coffee, the more tea, whatever you put in the water, the less light makes it through, right? So you could do a tiny, tiny drop of food coloring in a gallon of water. Oh, it's a tiny bit pink or whatever. Oh, if you dump the whole bottle, it's like deep red now. And it's like, okay, there's a lot of dye in there. It's something that's very obvious if we stop and think about it in that manner. But this is technically the math that goes behind all these experiments we do in chemistry, and then a lot of our detection is colorimetric, or we're measuring how much light is absorbed by the water by some solution. Okay, so that gives us an equation here, the log of the amount of light that made it through divided by the amount of light that we started with is equal to negative, and this is a molar absorption coefficient. I think I have a slide detailing all this. But it's basically how much light is a specific light absorbance times the concentration of that chemical times the length. So the x here could be L. So basically, what I'm pointing to here is this concentration dependence. So for example, this graph on the bottom is showing a couple of different natural organic matter sources. One is the Suwannee River natural organic matter. This one, I actually don't remember what that USR. A different river is natural organic matter. And this is, they have put the same amount of concentration in there, and we see one absorbs more light than the other. So and one thing to note is our UVC is right around here, right? So even though this organic matter doesn't absorb much light in the visible range up here, it might make it just look a little bit brown or, slight off color, yellowish, greenish, something. It's not impacting it much visibly, but it's absorbing a decent amount of our ultraviolet light that we want to pass through. So that's a pretty significant concern, and we could get some advantage if we, again, move the light, shift the light that we're using. Maybe we can get an advantage there. But in general, we want to know how much organic matter is in there, and a lot of times we use what's called specific UV absorbance. And we'll say oftentimes UV 254 absorbance as a guidance to know, okay, how much dosing we need. So if you ever see SUVA, that's the acronym that's used in kind of ultraviolet light realms. Okay, so we can account for all of that. We just need to have the measurements of the water and have some understanding, so that way we can know, okay, if our light in our reactor has to go, let's say, 6 inches to the end of the wall, and we want to design it for that, we have some amount of absorption due to our natural organic matter that's common in the river that we're treating, then we make that calculation and say, oh, okay, it's diminished by this amount, therefore we need to shine this amount of light through it in order to get a final dosing through the system that we wanted. Okay, so let's connect this to kind of rate equation. How are we going to define this in terms of a reactor of some sort? So really, this is going to be very much like what we call the Chick-Watson kinetics. This is going to be like dN dt is equal to negative k. We have the c to the n power times n to the 1 power, right? So that's we have some coefficient of specific lethality, the concentration of our disinfectant, and the amount of pathogens in there, right? That was our Chick-Watson kinetics. So this will be very similar. As we'll see. Okay, so in this case, instead of using a chemical disinfectant, we're using the dose of our UV light. We still have a first order decay reaction, so our rate here is still going to be a negative n to the 1 power. So this is first order, right, as we would expect. First order decay. Then we have our rate constant as some, I guess this is this parameter here, this is our coefficient of specific lethality for a given wavelength. And I actually don't remember what symbol that's called. Multiplied by our intensity of the light at that wavelength. Okay, so we have a coefficient of specific lethality and an intensity of that light at that given wavelength. So it's wavelength dependent instead of chemical dependent. It's also still microbe dependent. So it's specific to a microbe at a given wavelength. So very specific. And that actually follows that graph we saw a few minutes ago. I'll flip back there just real quick. Come right back to here. If you remember taking a look at this, this chart, we have these different organisms, and I guess they're not listed here, but each of those are a different organism, just like these are different organisms absorbing different light. And we can say, oh, at this wavelength, it's the coefficient of specific lethality, or that inactivation rate constant, is X amount. It's similar, but they will vary. And so that's specific to each microbe. And wavelength. I'm going to use lambda here as the wavelength. Okay, so overall, this is the rate of change, some number of organisms exposed to light at a given wavelength. N is that number of organisms. This guy here is the coefficient of specific lethality of that wavelength. The units there are going to be square meters per joule, whereas the intensity here is going to be the intensity of that light at that particular wavelength in watts per square meter. So what you notice when we combine the watts per square meter, so this will be watts over square meter times square meter per joule. Well, surprise, surprise, that turns into 1 over seconds, right? Things will simplify, and we'll be left with our very common first order rate constant units here as 1 over time. And in particular, since watts and joules are related by seconds, this is 1 over seconds. So what this means is our dose is really the intensity times time. Because this watts per square meter, that's essentially the energy received over time in some area, and then this square meter per joule is kind of how effective that is. How effective is the photon, that specific lethality. So really what we're getting is some amount of intensity over time. So our dosage we could describe then as intensity times time, just like we could describe our contact time as the concentration of the disinfectant times time. Our dose here in the UV sense is intensity times time. We could also call this fluence. So this dosage times time is like the contact time. Okay. Does that make sense? Any questions? All right. So just a little elaboration on the dosage here then. We could say that average intensity times time is perhaps the way to do that. So we say this dose, that's going to be, let's say, in millijoules per centimeter squared. Same thing as saying milliwatts times second per centimeter squared. And if we multiply that by time, then we get this if our intensity is that average intensity, then that all works out. Basically what I just said. And I think, is that right? Yeah. that's just an elaboration of what we just said. All right, so I'm going to give you an example problem. And as you'll see here, while I gave you a pretty technical explanation of the dosage and all that, usually when we're working a problem, it's fairly straightforward in terms of, oh, we just essentially need a rate constant, right? And so then we just need to look at the units to make sure we get a rate constant in appropriate units. And if you understand the concept of UV dosing is going to be a lot like chemical dosing, you need the amount of time and some amount of the UV together to get your result. It should end up feeling a lot like just a standard first order decay problem in some type of reactor. Okay, so this problem then says a company is designing a solar-driven portable water disinfection system to be used by the military. The system is simply an inlet tube, a pump, a well-mixed chamber, and an outlet tube. Okay, so first thing to do would be to draw that and decide what kind of reactor we're looking at. Water is pumped continuously into the chamber where it is irradiated by or with UV light before exiting through the outlet tube in a collection vessel. The disinfection rate constant for the UV light is 7.80 per second. And the bacterial count of the water must be reduced by 99.9%. Because the Army needs the unit to fit into a backpack, they require that the unit's chamber be no larger than 2 liters. How much water will the system be able to produce during 10 hours of sunlight? So solar driven. Okay, so give that a go. I'll give you a couple minutes to work that. so I'm going to go ahead and kind of walk you through how I would solve this problem. Stop me if you've got any questions. So first of all, I went ahead and kind of drew up a system, said we had a tube coming in, outlet chamber or outlet tube, and a well-mixed chamber, a pump sending it through the system. So that told me that it must be a kind of a CSDR of some sort. We have a volume, we have a K, and we have a ratio that we need to achieve in terms of the N over N naught, right? We need it to be a 99.9% reduction, meaning there's 0.001 fraction of the microbes remaining. So first of all, the K here is already in per time units. So I could have given you some sort of an intensity value, and then we would need some sort of a intensity times time, or something of that sort. But this is essentially our effective K. So what we would need if we were to look back for a moment. So K here that we were given is essentially the combination of those two, right? So all of that stuff that we talked about is already lumped into this problem, and we didn't actually have to know anything new, right? It's just the context here. So that was kind of one thing I wanted to show you is hopefully we should be able to solve this problem, whereas we could complicate it and say, oh, we have this coefficient of specific lethality, and I give you that, and this intensity, and I give you that. You could put those two together and get a per time unit for K, but that was already done, right? So this would be, sorry, not intensity, that would be specific lethality times intensity, right? Okay, so if you were to be given those in a problem, what you'd be looking for is to solve for a per time rate constant, just like we do essentially with chemical disinfectants, where we need to make sure that the concentration times the coefficient of specific lethality gives us a per time unit. Okay, so with that, I went ahead and set up a mass balance. I'm assuming this is going to be for a steady state, given that it just can be operated throughout the day. We're looking at a 10-hour time frame. That's what we're interested in. And the question is how much water can be produced. So I'm actually going to take an interesting approach here. So first of all, I set it up as 0 equals Q, Qn naught minus Qn minus Vkn. Now, I have two options here. I could solve for Q directly to get a flow rate, so that by getting a flow rate, that means I can get the answer, multiply that flow rate by 10 hours, right? That'll be my answer. Or maybe I should solve in a form where I know I can get it in N over N naught and use that to then solve for Q. Might be easier. So I don't know. So let's solve for Q first and see what happens. So I'll go ahead and put Vkn on the left here, and I'll factor out that Q, N naught minus N. So Q then is equal to Vkn divided by N naught minus N. So here, to simplify it, I think I could divide the top and the bottom on the right-hand side by N, and that might actually simplify us pretty well. So that would be Vk divided by N naught over N minus 1. So that seemed to do it okay. If N over N naught is 0.001, then it would also follow that N naught over N is 1000, right? So we could then say this is equal to Vk over 999. Okay. So that seems like a decent way to solve for it. And so then Q will be the V, which is 2 liters, times the K, which is 7.8. So something like 15 divided by 999. So we'll get a calculator out to do that. So 2 times 7.8. Divide that by 999. So the flow rate then should be 0.0156, and this is going to be liters per second because our volume is in liters and our time is in per seconds right now. So 0.0156 liters per second. Just right there. Okay, so we have a value for Q, and then we want to know how much water is produced over 10 hours. So we can take, we'll say total produced. It's 10 hours. We can go ahead and multiply that by 3,600 seconds per hour. And then multiply that by 0.0156 liters per second. And that should give us an answer in liters. So we'll just go ahead and take this, multiply it by 10, and then by 3,600. So that should give us 562 liters. Okay. Does that make sense? Okay with that? All right. So hopefully, once we stop and recognize, oh, this really is just a mass balance problem, shouldn't be too much issue, then I would recommend what you can do with this is think about, okay, well, what happens, what would these units look like? A coefficient of specific lethality and an intensity, and kind of take a look back to here to say, okay, maybe you could be given some number in these units, square meters per joule, and then intensity in watts per square meter. And by the way, that's pretty common, because if you think about how we would measure sunlight intensity, we're going to think about, okay, given this area, how much energy is coming to it over time, right? It's an amount of light that's being sprayed onto that square meter continuously over time, right? So that's the essentially the thing of it. Okay, so with that, I'm going to end this one and just give you a real brief run through of kind of some ongoing exploration of what happens when you have bacterial repair. So we talked about these things. And when I mentioned earlier this photolyase enzyme thing, there's actually some very interesting research which was ultimately awarded a Nobel Prize in 2015 for the discovery of this photolyase thing. And it turns out that the history here was this effect had been known for some time, that some bacteria could repair themselves after UV disinfection. In fact, you could look at the survival fraction as a function of how much UV was dosed. And if given some amount of time to recover in the dark or versus in the light, you would end up having more surviving if you were letting them recover in the light. So I think it was originally an accidental laboratory finding. It's like people disinfected some bacteria and then didn't measure them right away, left some out sitting in the laboratory light, and then, wait, they just repaired themselves? Like, what happened? So it turns out, eventually they realized that this thymine dimer thing could be a reversible reaction, essentially, by action of this photolyase enzyme plus blue light, or kind of slightly on the intense side of visible light. And so ultimately what the researchers wanted to do was they were like, hey, this is really cool. The bacteria have this innate ability to repair themselves. What if we could harvest whatever enzyme whatever chemical that's causing this? What if we could harvest it like we do with penicillin, right? Penicillin was famously one of our first antibiotics, and we produce it by harvesting it from microorganisms. We cause microorganisms to produce a lot of it, and they're essentially manufacturing it for us. So they're like, hey, let's do this. And so they went on to this investigation and ultimately realized that one E. coli cell only has like 3 to 5 of these molecules in it. So just a few molecules of this photolase enzyme thing was responsible for repairing like everything inside the cell. So it's just like they're going around there like crazy, activated by light to repair the cell. So ultimately they weren't able to manufacture it in that manner because they wanted to like add this to sunscreen, just like produce it, use it as a therapeutic for skin damage and things like that. Sounded like a really neat idea, but it ultimately did not work out. So they went into the kind of the mechanisms here, and it really is kind of neat that it's a photocatalyzed enzyme, so to speak. It's operated based on the light energy. It went all in depth in terms of like how it all works and how it's functioning with the cellular systems. And so one of the things that we've been studying in our lab is, well, what happens if we change from this mercury lamp to start using an LED instead? So we have a shift in our wavelength. We have some advantages for that, but there was an outstanding question. If this was our mercury lamp, kind of sketching the germicidal curve, approximating, and this is our UV LED now, we've shifted that wavelength, are we causing different damage? And does that mean the repair mechanism might change, given that previously it was mostly that thymine? Maybe we have thymine and then some other stuff, maybe more oxidative stress coming from this different wavelength. So we were kind of exploring what happens if we change from one wavelength to the other, because we know that some bacteria can repair themselves. That's already known, has been studied a bit. So there was an unknown about, well, what happens if we're disinfecting wastewater with UV light, and then suddenly we decide to change to this new technology? Are we causing a lot more repair, or are we getting maybe some advantage for less repair? Because it's a significant concern if we thought we disinfected the bacteria and ultimately they go out into the wild and then they're no longer disinfected, right? So this is just showing that we can kill the bacteria, and then here's what it looks like if we let them repair themselves over some time in the dark. So we had them kind of protected in a little dark chamber there. We gave some of them maybe some nutrients to grow on and all that. And essentially, if they were never damaged in the first place and they were just growing happily, this dotted line is what they would look like. That's kind of their growth profile if we did nothing but just gave them some nutrients and let them grow. So what happened is we first hurt them quite a bit. Some of them would repair pretty quickly. None of them really followed the normal growth. So there was some recovery here, but it was actually a lot different when we then gave them some of that blue light, or maybe slightly UVA light. And so then they would recover quite rapidly, whereas this bottom line is, okay, what happens if we never hurt them in the first place? We just shined this UVA light on them. It's kind of like sunlight, or the harsh part of sunlight. If we just shine that light on them, it kind of hurts them if they were never damaged in the first place. But if they were damaged and these maybe would have started up here, they went down to here, then this UVA recovers them quite rapidly over 3 hours. So that's kind of what we were taking a look at and saying, hey, well, what kinds of conditions affects this repair profile? And can we predict that? What types of parameters are going into that? And so ultimately what we're aiming to do with it, and what my current master student Andrea is kind of doing right now is modeling, okay, can we, based on this kind of like the types of concepts we've been covering, right? We have some sort of growth kinetics potentially. We have a decay kinetics that we could see from those bacteria that are being hurt. So there's some aspect of the UV light that we're giving them, the UVA, the blue light, violet light, I guess. It can hurt them a little bit. We've already hurt them with the UVC. So the question then is like, can we model that little bit of hurt, the repair aspect, but that repair aspect can only be from the amount that was actually killed in the first place, right? Or damaged in the first place. So it's like, it's not the N initial is not the full N initial. It's just the portion that were damaged. So it's kind of strange math. Somebody else has modeled it all, fortunately, and come up with some parameters, and then put it all together in a more complicated rate equation that has it doing something that's a little more like a polynomial. So it's something that actually these are fitting then to do that. So that's what we've been doing, is trying to see if we can predict exactly how many are going to survive at the end of the day if they're then given some, let's say, natural sunlight after disinfection. So it's kind of where our current research is going, and hopefully we'll be publishing some more of that work soon. Okay, so with that, I will let you go, and we'll get on to water softening and some things later, next time.